Hi. In the last section, we talked about linear and nonlinear systems of equations, and we solved some systems using the method of substitution. Today, we're going to look more at linear systems involving two variables. We're going to see how to use the elimination method to solve linear systems. And we're also going to talk more about what the possibilities are for the solution to a linear system of equations. And we're going to look at some examples of word problems. Okay, so here is an example of a system of equations that we could solve by the substitution method that we used last time, but it would get a little messy. If we were doing this by substitution, we would have to start by getting one or the other of these equations solved for either x or y. Like, for example, we could take the top equation, leave the 2x where it is, and subtract 3y on both sides, and then divide both sides by 2. That would introduce fractions, which is why I said this would get messy, but we could do it that way. But there is an easier way for this particular system, and that is to use the elimination method, which you may have also learned about under the name the addition method. So the way that works is we would just add these two equations together. The 2x and the 5x add up to 7x. The plus 3y and the minus 3y just add up to 0. And on the other side of the equal signs, the 18 and the 3 add up to 21. So that gives us the equation 7x equals 21. From there, we just divide both sides by 7, and we get that x equals 3. And remember, we're not done until we know both x and y. Now we know x is 3. We can go back and plug that in place of x into, well, either one of the equations. I just used the top one. 2 times 3 plus 3y equals 18. So that gives you 6 plus 3y equals 18. Subtract 6 on both sides, you get 3y equals 12. Divide both sides by 3, you get y equals 4. And now we have our solution. X is 3 and y is 4. And that does make both equations true. So a couple questions about what went on here. First question you might have is, why did this work? And the second question you might have is, why was this legal? Why are we allowed to add equations together like this? Well, the answer to the first question, why did this work, is that notice in one equation we had a plus 3y, and in the other equation we had a minus 3y. So those were opposites of one another. Same coefficient on the y's, except one was positive and one was negative. So when we added them together, they just added up to 0, and that eliminated the y's altogether. That gave us an equation with only one variable left. So that's why that worked, to add the equations together. The reason that's legal is we are allowed to add the same number to both sides of an equation. It keeps it equivalent to what we had before. So if 5x minus 3y equals 3, that means that 5x minus 3y and 3 represent the same number. They're equal. That means they're the same number as each other. So when I added 5x minus 3y to the left side of 2x plus 3y, the top equation, and I added 3 to the right side of that top equation, I was really adding the same number to both sides, which is a perfectly legal thing to do. Now let's look at another example. Here are two equations that make up the system are negative x plus 10y equals 3 and 5x minus 11y equals 24. And if we add these two equations together, it doesn't really help. The negative x plus 5x adds up to 4x. The plus 10y minus 11y add up to minus y. The 3 plus 24 add up to 27. And so we get an equation that still has both x and y in it. We already had equations that had both x and y. Getting another one doesn't really get us any closer to figuring out what either x or y by itself has to be. And the problem was that this time, unlike the last time, the coefficients on the y's were not opposites of one another. What we want to do is get it so that the coefficients in front of the y's or in front of the x's, either one will work, but we want the coefficients on one of the variables to be opposites of one another. And in this case, the easiest way to get that to happen is, notice we've got a 5 in front of y on the bottom equation. I would like for there to be a -5 in front of the y in the top equation. And to get that to happen, I am allowed to take an equation and multiply both sides by the same number, as long as that number isn't 0. So if I multiply both sides of the top equation by 5, so everything on both sides gets multiplied by 5, turns it into -5x plus 50y equals 15. So I multiplied the top equation by 5 on both sides. I didn't have to do anything to the bottom equation. I just slid it over so it would be underneath the new version of the top equation. And now I am ready to add these two equations together. The -5x and the +5x add up to 0. So the x's kill each other off. There's no more x's left. The plus 50y and the -11y add up to 39y. And the 15 and the 24 add up to 39. So the equation we get is 39y equals 39. Now I can divide both sides of that by 39, and I get y equals 1. And remember, we're not done yet. That's only half of what we need. But we can take that number, y equals 1, and stick that 1 in place of y in either one of the equations we started with. I decided to just use the top one, so I get -x plus 10 times 1 equals 3. That would just be -x plus 10 equals 3. Subtract 10 on both sides, you get -x equals -7. Divide both sides by -1, you get x equals 7, and now we have our solution. 7 for x, 1 for y. And that does work in both equations. -7 plus 10 times 1 equals 3, and 5 times 7, which would be 35, minus 11 times 1, 35 minus 11 does equal 24. So let's stop and talk about how this method works in general. First of all, the two equations need to be both lined up the same way. So if they aren't both lined up in the same way, with the x terms and the y terms and the equal signs and the constant terms in the same positions in both equations, you might need to do some rearranging to get that to happen. But then once they're both lined up the same way, you need to obtain coefficients for x or y that differ only in sign. That is, the numbers in front of the x's or in front of the y's have to be the same except for one of them being positive and the other one being negative. And the way you make that happen is you multiply everything on both sides of one or both equations by whatever number it takes to get that to happen. Then you add the equations together to eliminate that variable. The result of doing that should be an equation that only has one variable left. So you go ahead and solve for that variable, and then take the number you get and substitute it back into either one of the original equations and solve for the other variable. Now, usually when you have a system of two linear equations, where the graphs of the two equations are straight lines, usually those two lines intersect in some particular point. And then that point, the coordinates of that point, would be the solution to your system. So in that case, we would say the system is independent and consistent, and it would have exactly one solution. But there are other possibilities. One thing that could happen is that your two equations really represent the same line. They really are equivalent to one another, so that any point that's on one line is automatically also on the other line. Any pair of numbers that works in one equation will also work in the other one. In that case, instead of just getting one solution to the system, you have infinitely many solutions, because any point along that line is a solution to both equations. We call that a dependent system. And the way to recognize when you've got one of those, well, one way to tell is if you graph the two equations and they turn out to be the same line. But another way to tell is if you're trying to solve the system by either the substitution method that we talked about last time or the elimination method that we talked about now, and you eliminate both of the variables, you end up with something like 0 equals 0, just an identity. That's how you know you're dealing with a dependent system. The other thing that could happen is that both variables get eliminated, but you end up with a contradiction, something like 0 equals 1, that just plain is not true. And that means that you have no solution to your system. It's an inconsistent system. And that means that the two equations represent lines that are parallel. They never cross. They don't have any points in common. Let's look at an example. Let's say we have the system 2x minus 4y equals 12 and 3x minus 6y equals 16. And I decide that to make the x coefficients opposites of one another so that they will add up to 0 and eliminate the x's, I'm going to take the top equation and multiply it by 3. That will give me a 6x here. And I will take the bottom equation and multiply by negative 2. And that will give me a negative 6 in front of the x in the bottom equation. So when I do that, everything on the top equation gets multiplied by 3, and I end up with 6x minus 12y equals 36. Everything in the bottom equation gets multiplied by negative 2. So I end up with negative 6x plus positive 12y equals negative 32. Now when I add these two equations together, the 6x and the negative 6x add up to 0, and the negative 12y and the positive 12y also add up to 0. So everything on the left side just adds up to one big 0. Meanwhile, on the other side, the 36 and the negative 32 add up to 4. So what we get is the equation 0 equals 4. Now that is just plain not true. We have a contradiction here. But what that tells me about this system is that the system is inconsistent. There is no solution to the system. And if you graph the two equations, you would find that they are parallel lines. Anything on the blue line would work in one equation, anything in the red line would work in the other equation, but there's nothing that works in both equations at the same time. And here's a slightly different example. Here the two equations are 2x minus 4y equals 12 and 3x minus 6y equals 18. Again, I'm going to multiply the top equation by 3 and multiply the bottom equation by negative 2. And now when I add the equations together, I get 0 equals 0. The numbers on the right side this time add up to 0, and so I get 0 equals 0, which is true. That's an identity. That's true no matter what. And that tells me that there are infinitely many solutions to this system. Anytime one equation is true, so is the other. We say that's a dependent system. So if we drew the graphs of those two equations, they would turn out to be the exact same line. Any point on one line is automatically on the other line. So for example, 6, 0 works in both equations, 0, negative 2 works in both equations, and so on. There are infinitely many possibilities.